This is the second session of our Aero modeling workshop, which is Aero Plus, and its topic will be flight principles, and it will be taken by our technical member, Samir Ranjan, who is a technical member at phoenixaero and is a second year student of Department of Mechanical Engineering at SVNIT. So yes, Samir, you can start.
So good evening, guys. These are the session objectives of uh, today's session. So in today's session, you'll learn about how lift is generated, role of an airfoil in designing a plane, comprehend the structure of wing, and understand different compartments of the aircraft. So in yesterday's session, you learned about the four basic forces acting on an aircraft, that is thrust force, lift force, drag force, and weight, obviously due to gravity. So today we'll basically focus on the lift force, how it is generated, and what all theories are there behind it. So can anyone explain me like how lift is generated in a very brief manner? Anyone, guys, you can unmute yourselves and speak up.
Sir, it's
Yeah.
due to speed. Sir, it's due to speed of turbines which helps them to flow
The
water.
pressure difference.
Actually, it is
Pressure
due to the
difference.
pressure difference
Pressure difference.
of air, speed of air below the wind. Sorry,
Yeah,
So
close
below
enough.
Bernoulli's
the wing
principle
is
basically
high.
governs, and due to this, pressure difference is generated, and due to that, lift is generated. Basically,
Okay. You
yeah.
all are close enough, but I want the precise answer. So, okay, so let's see in detail like what's exactly behind it.
Bernoulli is given the equation
So,
which
there are,
Sir, half rho v square wali wo.
exactly. Okay. So, there are different lift theories which which tell us how lift is generated. So, one of them is Bernoulli's principle, which some of you already said, and it was given by Daniel Bernoulli. So it states that an increase in velocity of any fluid is always accompanied by decrease in pressure. So let's connect you to your +1, +2 levels. So you all might recall that when you blow any wind in between two balloons, then it will come closer, and that's because of the Bernoulli's equation. So now let's see like how it helps us to generate lift in any aircraft. So as you could see, like this is the cross section of the wing, and here it is p atmospheric, and here also it is at p atmospheric. So to maintain the atmospheric at both the ends of the wing, the stream has to travel from the upward surface of the wing and the lower surface of the wing. So in this particular slide, you could see the upward surface of the wing has larger distance as compared to the lower surface, and that's why the wing has to travel a bit faster than the lower surface, which creates a low pressure region in the upward surface and a high pressure region in the below this wing. So which eventually, because of Bernoulli's theorem, which eventually creates an upward force, and that we call as lift, that we call it as lift. So this was one of the theorem. Next theorem is like Newton's third law, which you all know from the ninth standard itself, and that is every action has an equal and opposite reaction. So let's see how it helps in explaining lift generation. So this you could see, this is the cross section of a wing, and you all know that force is equals to mass into acceleration, and this actual acceleration is if we break it, it is basically dv by dt. So this velocity is a vector quantity, and hence force is also a vector quantity. So if we change the direction of this velocity, then also it will there will be a change in force. So as you could see, this is the relative wind direction in any this wing cross section, and as it encounters any wing, it deviates in downward direction, it bounces down, and due to this there is a net momentum change, and that's why it generates an upward force, which we call it as lift. Then there is one more theory, which is basically it is Coanda effect. It was given by Henry Coanda. It says that jet of fluid has tendency to stay attached to the convex surface. So let's see what it is in detail. In this picture, you could see there is a flow of wind which is approaching any spherical geometry. So what happens is the flow which is coming in this particular region, it gets blocked because of this geometry. But the flow which is just gracing the surface has a tendency to bend towards the surface and moves in this pattern. So as it moves in this pattern, these stream flow pushes the air particle present here, and this creates a low pressure region in this area. And due to this pressure difference, a force is generated in this direction, and hence if we see the same phenomena in the case of our wings, then it same thing happens, that as you could see, the stream flow is moving in this direction, and it is pushing the air particles in this region. So due to this, a force is generated upwards, which we call it as lift force. Then all these theories could not explain why lift is generated, because all of them had some controversy, some demerits, and let's see it one by one. So first of all, Bernoulli's principle, why we couldn't explain lift generation all with the Bernoulli's principle. That's because he stated that, like, first of all, we stated that the air particles here and the air particles here will travel in equal time, and we call it as equal transit theory. But it was a flaw, because after further researches we found out that the particle here and here are not traveling at equal times, as you could see in this GIF. If you could like notice, this red particle has traveled forward, but the lower particle are like lagging behind. But in spite of that, the pressure which is maintained here and the pressure which is maintained here is constant. So we can explain lift generation with this Bernoulli's principle, but we cannot state that it travels in equal time, and that's why the velocity in upward surface is like higher, and the below surface is like it's lower. So this was one drawback of Bernoulli. And in the Newton's third law, few wind tunnel tests showed that if we keep a wing section in any like airflow, then also it was generating lift in upward direction. Like this was the wind velocity direction, and if we kept this wing cross section in that wind tunnel, then also it was generating upward direction. And Newton's third law couldn't explain this. Like if only and only if it is bouncing in this pattern, then only it can generate lift in upward direction. But in here but in this case, Newton's third law was incapable of explaining why this was happening. Then like controversy, like you could say it was a flaw of Coanda effect, that it was like not explaining what's happening at sharp edges. So if you if you blow air in the upward surface of a cuboidal box, then it won't bend here. And why this was happening was not explained by Mr. Coanda. So that's why this theory was also not fully accepted. Then after all these things, few researchers like Mr. Lanchester in the year 1809 came up with a mathematical model. And after 10 years of that, Ludwig Prandtl came up with the somewhat similar mathematical model, and it was lifting line theory. So like it was a mathematical model that predicts lift distribution over three-dimensional wing based on its geometry. So what basically was like in all the previous theories, you have seen that they were calculating lift on 2D section, but in this mathematical model, they calculated the lift on the whole wing. So what they did was they considered that the lift not only depends only on a particular 2D section, but the 2D sections adjacent to that particular section. So it depends on the cross section at an x and x plus dx. So from that they made a mathematical model and the distributed lift, and then he calculated like what exactly how much lift we can generate from a particular wing. So further researches are going on this theory as well, and but for now we use this theory in researches and everything. So like I showed you many shapes, huh? So what are these weird shapes and why are we using them? First question, like from where did they get originated? So for to get to know this, let's learn about another effect. So one of this study showed that if we rotate a cylinder with a particular omega, then it was generating an upward force. So like out of curiosity, scientists drew the FBD of this particular cylinder. So they found out that if we blow wind from this direction in a static like over a static cylinder, then it was generating this type of forces due to the interaction of air molecules and the surface of cylinder. So it all got cancelled out, and hence no force was generated. But when they gave it a particular omega, and after giving it a particular omega, when after like when they blew wind from this direction, then they noticed that it was generating somewhat force upwards and some force downwards, but this time there was a net force in the upward direction, which eventually like made them think like how can we do this without giving it an particular omega. So like after few more studies and after few things, they came up with this type of geometry which is called an airfoil or aerofoil, which is in this shape. So the uh, benefit of this shape is like we can generate same amount of upward force without giving any omega to this geometry. So this was like considered to be used in wings or any things which could like which from which we wanted some type of lift force. So let's see like what are the different terminologies or how we can differentiate between these different shapes, which is airfoil. So the front end, which you could see, this part is called the leading edge, and this part, which is the back end, is called the trailing edge, and the line joining the leading edge to this trailing edge is called the chord line. So the line joining this line is called the chord line. In this slide you can clearly see this is the leading edge, this is the trailing edge, and this is the chord line. Now as you could see, there is like a curved portion upwards and a curved portion below. So when you connect these 2 points from the upper and the lower surface and divided by 2, you'll get one you'll get a set of points, and if you like connect that set of points from the leading edge to the trailing edge, then you'll get one line which is called the camber line. So this particular line is called the camber line, which if you want to say in layman's language, then it is basically the curved part, like how much curved the airfoil is. How much curved the airfoil is, that's significance of camber line is that. So in this slide, you could see, like I already explained you, this camber line and this chord line. So in any airfoil, you'll find one like maximum portion of maximum camber position. Like this is the point where the camber is maximum. In the whole airfoil, you'll find this camber is like somewhat increasing from here to here, and from here it is decreasing. So there is one point, like one maxima, and that distance from the leading edge is called the maximum camber position. Same for this thickness, the position of from the leading edge to the maximum thickness position is called the is called the maximum thickness position. And the front, like radius of curvature of the leading edge, is called the leading edge radius. Like these things are not much used in day-to-day things, so it's only like few jargons of aviation sector. So these things are there. And now one question arises: what if airfoil is at an angle? Like what how will it behave in any wind velocity? So first of all, let's see what's that angle is. So this the angle between relative wind and the chord line is called the angle of attack. And this the lift force is directly proportional to the coefficient of lift, which is somewhat like linear, has a linear relation with angle of attack, that is alpha. So as you increase this angle of attack, the lift force which is generated is increased. This we have this is the came out in different experiments, that as we increase the this angle of attack, the lift is increased. Now one question arises is, what will happen to lift if we increase the angle of attack to 90 degrees? Anyone?
Stall.
So what exactly stall is?
Sir, retardation of speed.
Okay. Okay.
Those wind lines breaks and there is no
Okay.
lift.
Close enough. Very good. Very good. Very good. So let's see what stall is. And so basically, as you could see in this GIF, there is an airflow separation from the upper surface of the wing, and hence there is a turbulence formed here, due to which there is no it cannot generate lift force in this condition, and hence the aircraft comes under free fall. So that stall is. Now, every airfoil has a particular stall angle. In this condition, it is 20 degree, and after which the stream flow above at the above surface of an airfoil is separated, and it creates a turbulence due to which it is incapable of generating lift. So it is advised to keep the angle of attack below than this critical angle, and so that the stability of an aircraft is maintained. Now let's see different types of airfoil. As you could see, this is a symmetrical airfoil, symmetrical about this x-axis or the chord line. So it is equally thick in above and below, and it is used in it is basically used in the at places where more stability is required. So at the tail part of the aircraft or at the vertical tail part of the aircraft. Then this airfoil is a bit thicker in size, so it can be used in fuselage where we want to generate lift, and it is like here also we can use it in different turbine blades too. Now these type of airfoil is like highly cambered one and thin airfoil. So these type of airfoils are used in like fighter jet wings where we need to reduce the weight of the wing, and also we want high lift. Then this is like a special kind of airfoil, and this is in this airfoil you could see the trailing edge is bent upwards, which is like because of which it can also generate a negative torque to counterbalance the nose down moment, like when any aircraft flies. So it is basically used in fighter jets. As you cannot see in some fighter jet, there are no empennage, so like no tail part. So this airfoil is used so as to like when any lift force is generated, to counterbalance this you need one tail part. But in some fighter jets we use these type of airfoils to counterbalance it, to self correct that nose down moment. Now we'll see how airfoil can be used in wings. So as you could see here, like it is the picture of a wing while in manufacturing condition. So this is what it looks like, and these are all like cross section of a wing. So let's see about few terminologies of the aircraft wing. As you could see, the distance between the two extreme positions of the wing is called the wing span, and the length of the cord of airfoil at the tip of the wing. The airfoil at this position, the length of that cord is called the tip cord, and the length of the cord present at this position is called the root cord. So when we add both the two and divide it by 2, so root cord plus tip cord divided by 2 gives us MAC, which is mean aerodynamic chord, which is somewhere which like lies somewhere here. So all the calculations which we do are done with the mean aerodynamic chord. Now you might have heard about the term aspect ratio. So like in pictures also the term is aspect ratio is used, but in aircraft it has a different significance. So the aspect ratio is the square of wingspan divided by the wing area. So if you take a rectangular wing and suppose its chord length is C and wingspan is B, so the aspect ratio becomes B square divided by B into C, cancelling this out. So the aspect ratio comes out to be B by C, which is like this C is mean aerodynamic chord, MAC, which I already explained you in the previous slide. So these two formulas we use for calculation of aspect ratio. Then there is one question for you all, like what types of wing shapes have you seen? Like, what different wing shapes have you seen? Anyone? Come on, guys. Like, in this picture, like in this presentation, only I have shown one or two.
Guys, you can unmute and speak.
सर मैंने दो देखे हैं
Okay, which shape?
सर नाम तो नहीं याद पर वो थोड़ा एक बैंड टाइप था एक और
Okay.
एक सीधा वाला जो प्राइवेट जेट्स में होता है प्राइवेट जो होता है ना उसमें वो
Okay.
सीधे वाला था और कमर्शियल फ्लाइट्स में थोड़ा बैंड वाला आया था देखा था मैंने
Okay. So the one which you were talking about was like swept back wings, and
Delta wings.
this like somewhat just now said delta wing. So this is delta wing. So in technical term, we call it as wing planform. It is not called shape. It is called wing planform. So there are different wing planforms as per design requirements. So somewhere we have trapezoidal, somewhere we have triangular, which is called delta wings. Somewhere we have somewhat like ellipse.
Pentagonal.
Hence, like, so we have different like shape planforms as per design requirements. Then this is the internal structure of the wing, how internal of a wing looks like. So we cannot make a solid wing, as it will increase the weight of the wing and it will eventually break off from the fuselage. So that's why we to give it proper structural strength and to decrease its weight, we use this kind of internal structure. In this you'll see there are plate sort of thing which is called ribs, and these plates are attached by rods which is called stringers, and over these whole this whole system we put up like a skin which you see from naked eyes, which is you have seen like in previous slides. So this is what internal structure of wings look like. When we talk about commercial aircraft like Airbus or this Boeing 1747. So this particular compartment is there for the fuel. So they store fuel in their wings. Now you all might have traveled from the aircraft, so you all have noticed like these type of formations take place in the sky when an airplane flies. Like you go from the window seat, if you have noticed, you can see these type of formations. It is called contricles, and from the plane point of view, you could see this thing. Like we usually don't get a chance to see this, but we might have noticed like these contricles. So can anyone tell me like why this vortices are formed? It is generally called wingtip vortex. So can anyone tell me why these vortices are formed?
sir condensation
No.
of air molecule
Somewhere you're close.
अच्छा वो ऐसे विंग के टिप्स पे अचानक मतलब ऐसे ऊपर में लो प्रेशर होता है और नीचे में हाई प्रेशर होता है तो एयर टर्न होके ऊपर की तरफ जा रही होती है
Exactly. So what happens is here is a low pressure region and here it is a high pressure region. So in the middle of the wing, an upward force is generated, which is called lift. But at the edges, the wing tries to move upwards from this direction, from the side direction, and this initiates an upward stream flow of the wind, and that's why this wingtip vortexes are formed. And so like why this vortices are like not necessary. So it generally reduces the efficiency of an aircraft, it increases drag, and it reduces the efficiency of an aircraft. So if it decreases the efficiency, then how can these vortices be reduced? Can anyone tell me like how can these vortices be reduced?
Sir, some planes have curved edge. Means
Okay.
their edge are curved.
Bent part.
Okay.
At the end.
What is that bent part called?
Winglets.
Winglet, yes.
Very good, very good. So these vortices are reduced by these attachments, which is called winglets. So what difference this winglets do is they try to prevent this the motion of winds from the side edges. So in this way, they decrease like the drag and also decrease the vortex formation. Now, in yesterday's session, you have learned about there are three parts of any aircraft. One is wing, one is the second one is fuselage, and the third one is the tail or the empennage. So this fuselage part also has a few manufacturing few like terms. So first structure is called the welded steel structure. In this, they use horizontal rods, basically the steel rods, and which is called longerons, and they use diagonal rods, which is called struts, to make a truss type of structure and to give it a structural strength. Nowadays, it is not much in use, but previously this was the only structure which was used by Wright brothers, and it is now, I think it is only restricted to some trainee aircraft or all those inexpensive aircraft. So after this, the scientists came up with another fuselage structure, which is the monocoque structure. In this, they use a bulkhead, a plate sort of thing, and a ring, which is called formers. And above, like around this, they wounded skin. So what it did was it distributed the stress in radial direction, and hence, like, it was beneficial. But in the flaw in this structure was it couldn't distribute the stress in longitudinal direction. So there might be a possibility that it might collapse in this direction, and hence, like, our aircraft would fail. So they fused the above two structures, the welded steel truss and the monocoque, and they formed a semi-monocoque structure, in which they used this longerons and stringers to attach this bulkhead to distribute the stress in longitudinal direction and the radial direction, and over it they wounded the skin, so as we can even keep few payloads, or nowadays it is used in this commercial aircraft. Now the third part, which is the empennage. So why do we need an empennage in any aircraft? So let's suppose this is an aircraft, this is the wing which is generating lift, and there might be a possibility that the force which is generated in this upward direction can create a torque at any point in this manner, and hence our aircraft would get unstable. So to counterbalance this torque, the empennage is designed to generate another force in this direction, so that the aircraft is stable and these both the torques are cancelled. So there is a fun fact that like the fatality rate in any commercial aircraft is only 32% at the back third of a fuselage, and around 38% at the front two thirds of the aircraft. So from the next time when you book tickets, like, try to book at the back end of the aircraft. So now there is one question, like, can we stabilize a commercial aircraft without an empennage? Guys, come on. Unmute yourself.
By managing the weight distribution.
Somewhat close, but no. Like, think more on this. Anyone? You can also write in the chat box. So okay, so let me answer this. We can stabilize a commercial aircraft without an empennage, but in the commercial aircraft, the main focus is to give comfort to any passenger. So if we use any reflex airfoil in commercial aircraft, then it will automatically stabilize itself, but the comfort which it can provide to the passengers is not that great, like in comparison to any aircraft with an empennage. So to give that much comfort and stability to any aircraft, we use an empennage.
Sir, what is reflex that you told?
In the previous slide, I already explained that it is bent at the trailing edge, so it gives it like there is no requirement of empennage in that design, in that aircraft, so it automatically corrects itself. So we'll see this at the end of this session.
Oh.
So let's continue with the slide. So now empennage also has control surfaces. In the last session, you have learned about the control surfaces on the wing, so ailerons. But at the empennage also we have control surfaces. Those are the rudders and the elevators. So there are two parts of any empennage. One is the horizontal part, and the other one is the vertical part. So the vertical part is called as vertical stabilizer. The horizontal part is called the horizontal stabilizer. And in case of rudder, if we want to move the plane in upward direction, then we have to deflect this elevator in such a way that it will pitch up. And if we want to yaw this aircraft, then we'll have to deflect this rudder in the opposite direction, so that it will move like it will turn with the yaw axis, which is basically the y-axis, if you like imagine this plane. So next question is like, what different configurations of empennage have you seen? Like you all are aviation enthusiasts, so all might have searched different configurations of empennage. Or anyone? Any names? Okay.
I haven't seen, sir.
No problem. So like these are different types of empennage. Like this one.
Sir, V-shaped.
Mm-hmm.
Sir,
Yeah.
I know two V-shaped and inverted V-shaped.
Okay. So this you could see here, it is V-shaped, which you're talking about. And this all empennages are designed on the basis of design requirement, like what do we exactly need from that aircraft. So this is Y-tail, this is twin tail. It is basically used in like fighter jets only. This is V-tail, this is T-tail. As you could see, it is in the form of a T. This is inverted U-tail with boom rods. This inverted U with this boom rods. And here it is H-tail, this with boom rods. And in this you could see it is only H-tail, which is directly mounted on the fuselage, this thing. So it is simple H-tail. Again here it is inverted U-tail. Now this is somewhat like fusion of conventional tail and the T-tail. So it is like horizontal stabilizer is attached at the mid of the vertical stabilizer, and which forms a cruciform tail. So these are the different types of empennage. Now the question of the day, as I already said, that in any wing, we need to reduce the drag so as to increase the efficiency. So you all might have traveled from the aircraft, and like you all have seen these type of protrusions on the wing. So these might increase the drag on the wing and decrease the efficiency. So why these protrusions are present there? Like, what is the use? You can answer this question on the Discord channel, and we'll entertain all your answers. Now, from this, we come to the end of this session.